Welcome back, class. Last week, we used the Excel function linus to do simple regressions to estimate the equations relating m to each of our three explanatory variables, gr, ge, and in. Each of these regressions reported the percentage of the total variation in m explained by each of the three variables. And when we added up those percentages, we got a combined percentage of 65%, suggesting that together, gr, ge, and in explain 65% of the total variation in m. But I then said that if there's any correlation among the explanatory variables, we can't conclude that together they explain 65% of the variation in m, because correlation among explanatory variables results in double counting of their combined explanatory power. Part of the variation in m that is explained by one variable is also explained by a correlated variable. It turns out that there is virtually no correlation between gr and in, or between ge and in. However, the correlation between gr and ge is minus 0.34. which is moderately strong. The negative correlation means that as gr increases, ge decreases on average. Perhaps that's because the weaker our rider is genetically, the harder he pushes himself to compensate. But whatever the explanation, the result of the correlation is that summing the three individual EVs gives a biased estimate of their combined EV. And as we shall see, because the correlation is negative, this bias underestimates the combined EV. The solution to the problem of correlation among explanatory variables is multiple regression. In multiple regression, linus estimates the coefficients and the constant for a single equation that includes all the explanatory variables. It looks like this: m equals a times gr plus b times ge plus c times in plus k plus e. Now, I can't show you an xy plot of this equation in three-dimensional space because the equation involves four variables. Fortunately, linus has no problem at all working in 4 dimensions, or 40 for that matter. In a multiple regression on an array of m, gr, ge, and in, linus calculates coefficients for each explanatory variable and a single constant. It also calculates the explained variation of all three explanatory variables combined with no double counting. Here are the results. The coefficient of gr equals 1.8, coefficient of ge equals 1.3, the coefficient of in is 4.4, and the constant is 6.2. So here's the equation for m that linus estimates using multiple regression. Now, the coefficients and the constant in this equation aren't the same as the ones we saw in the simple regression equations. This is because multiple regression estimates coefficients for each of our three explanatory variables while holding the other two constant. This doesn't happen in simple regression, where the effect of unincluded variables creates noise that distorts the equation estimated for the included variable. Let's now look at the combined EV of the independent variables in the multiple regression. Linus doesn't report a separate EV for each explanatory variable. Instead, it reports a statistic called R squared. R squared is the ratio of the combined EV of the explanatory variables to the total variation in the dependent variable. For this multiple regression, linus gives an R squared of 0.77, which means that the equation explains 77% of the variation in m. Now recall that last week, when we added up the EVs from the three simple regressions, we found that combined they explained 65% of the total variation in m. But here, the multiple regression is telling us that the combined EV is 77% of TV. The sum of what the variables explain separately in simple regressions is less than what they explain together in a multiple regression. This is the result of the negative correlation between GR and GE, which results in negative double counting of explanatory power. And the result of that is that simple regressions underestimate the combined explanatory power of the three variables. Now, before I let you go, I want to answer the question posed in the title of this course. Which matters most in explaining the outcome of the rally? Grit, genes, or privilege? One way of answering this question is to perform what I call the lost variable test. Here's how it works. Linus reports that for the multiple regression, including all three explanatory variables, the combined EV is 1,160. How much of this EV is lost when we exclude one of the three variables and run the regression with just the other two? This is the lost variable test. When we do the test for each of the three explanatory variables, here's what we find. When we exclude IN and run the regression on GR and GE, combined EV drops by 34%. When we exclude GE and run the regression on GR and IN, EV drops by 25%. And when we exclude GR and run the regression on GE and IN, EV drops by 55%. Which means that grit matters more than genes or privilege in explaining how well riders performed last summer. And privilege matters more than genes. So far in this course, we've been using our regression equation to explain the results of last summer's rally. You're probably wondering whether we can use the equation to predict the results of next summer's rally. The answer is yes, and next week I'll show you how. See you then.